Hello, everyone. Welcome to today's coaching seminar. It's my pleasure to introduce Rémi Jaoui from Université Claude Bernard Lyon 1. And he'll tell us about on the problem of integration in finite terms and exponentially algebraic functions.
So thank you for the introduction, and thank you all for coming. So if you have questions, please stop me. I cannot see the chat, so if there are questions in the chat, if someone can tell me, then I will answer them too. So I'm going to talk about a project that we started with Jonathan Kirby 2 years ago. We are still finishing writing up the paper, and we hope it will be out soon, but I will try to present you the main result. And so first of all, what my talk will be about. So my talk will concern model theoretic extension of what is called the classical problem of integration in finite terms. So the problem of integration in finite terms was studied by Liouville first, so in a period from 1833 to 1841. And what I put here on my slide is the solution of the problem of integration in finite terms. That was, so it's just a note which was published by Risch in 1969. And so so I'm following what he says, is that the problem of integration in finite terms, it asks for an algorithm for deciding whether an elementary function has an elementary indefinite integral, and to find such an integral if it does. And so, as he says, this vaguely worded question has several precise but inequivalent formulations. So we will see another formulation than the classical one, but here he says that the writer, so Risch, has devised an algorithm which solves the classical problem of Liouville, and so it's a paper of 1969, and the complete decision procedure, which was planned for future publication, was only published recently in a volume by Raab and Singer. Okay, so to give you a little bit more idea about what I'm going to talk about, I will start with an example, and I will try to say that the original motivation was not only to compute integrals, but to compare different problems from classical mechanics. So I put you two famous problems from classical mechanics, one where you know how to solve the solution, the harmonic oscillator, and one where you don't know how to write down the solutions, which is the equation of the pendulum. So you see the equation of the pendulum is not even an algebraic differential equation, but it's almost one. If you make a change of variables, it becomes algebraic. So what you can do is, first of all, so there are equations of order 2, but both systems so preserve the energy. It's a common feature in many systems in physics. And so you can write down the energy of the two systems and restrict to a given level of energy. Okay, and in that form, instead of having order 2 equations, what you will end up with is order 1 equations. And what I told you before, if you make this change of variable that is written here, u is equal to cos theta over 2 in the first one, although the equation is not algebraic and the energy is not algebraic, what you end up with is an algebraic equation. Okay, it's actually an elliptic equation. And in the second one, you also have an algebraic equation. You don't need to change variables. Okay, and so what you can do from there, you can see that you can use the method of separation of variables. And so what you do is, instead of trying to solve u instead of z, or u in terms of theta, what you're going to try to solve is z in terms of u and z in terms of theta. Okay, and what you end up with is to compute just an integral. Okay, and this one is an elliptic integral in the left-hand side, and the right-hand side is, okay, you can compute the integral explicitly, it's the inverse trigonometric function, and this is why you can compute the solution of this equation. Okay, and so the purpose of my talk will be to present you a version of the problem of integration in finite term when one can use at the same time the kind of decision procedures to compute integrals that Risch was talking about in the previous slides, but one can also perform at the same time geometric operations, such as changing the variables, what I did here, okay, and change of the independent variable, what I did in the second part. Okay. So that's the purpose of my talk. So my plan is first to talk a little bit about the classical problem of integration in finite terms. I won't spend too long on that. And then to explain what we are changing from the classical problem, so it's the notion of exponentially algebraic function, and then I will present our results. So what is the classical problem of integration in finite terms? It's based on the notion of elementary function. And so what is an elementary function? So if first we think about the element as function, so an elementary function, first of all, it's an holomorphic function. We are not working in a real setting. We are working with holomorphic function, and which can be constructed, so somewhere, maybe not everywhere, okay, on some non-empty open subset of its domain. Using the following operation, you're allowed to use the arithmetic operation. You can add, multiply, divide two elementary function, and you will get an elementary function. And I'm stressing that I'm allowing arbitrary complex numbers. Okay, so there is a version over Q bar. I will just look at the version over C. Okay, and then you're allowed to take your elementary function and post-compose them using the complex exponential and branches of the logarithm. And finally, you're allowed to extract roots of arbitrary algebraic equations. And so here I gave you three examples that are interesting for different reasons. And the first one is to show you that you're allowed to use many operations. In some sense, you can build very complicated functions. The second one is just to show you that the arcsine functions, the inverse trigonometric functions, they are elementary functions. The trigonometric functions are also elementary functions. And the third example, this cosine of square root of z, is an example where you actually need to restrict the domain of definition. If you think about this function, it is an entire function because the cosine, its power expansion has only non-zero coefficient in either power of z. But in order to witness that it is an elementary function, you will need to restrict the domain of definition. And let me just give you a word of warning. If you try to work with functions, it's in the paper of Reed, or the book of Reed on the subject. I like this quote a lot. It says that there are, however, certain questions connected with the many valued characters of elementary functions, which could be pressed back behind the symbols in Newville times, but which has since learned to assert their rights. Such matters are mulled over in the first chapter. So it might be great fun to talk about elementary function as if they were one valued. I might even sound convincing to some readers, but I certainly could not fool the function. Okay, and you can see these kind of things when you write this kind of equality. Okay, what do you mean here? Okay, well, here it's a function, here it's another function. What is this equality here? Okay, so you have to be a little bit careful. And one way to be careful, we are in a seminar about differential algebra, is to use differential algebra instead of using function. Of course, one misses a little bit of things with this framework, but this is what I'm going to do. And the advantage of the differential algebraic definition, the second advantage, it's also that it's a relative notion. Okay, you can work over any base differential field. Okay, while the first notion is an absolute notion. And so instead of defining the notion of elementary function, you're going to define the notion of elementary differential field extension. And so differential field extension is elementary, so unconstrained in the sense that it doesn't have new constants. Okay, so I'm always assuming that my elementary differential field extensions have no new constants. If you can find a tower of differential fields, okay, such that each one, so what replaces the arithmetic operation, they are automatic because you work with fields. What replaces precomposition by the complex exponential and the logarithm is that you're allowed to adjoin an exponential, namely an element, which is solution of a differential equation of this form, or a logarithm, it's the opposite of the differential equation I wrote. Okay, and what corresponds to extracting roots of arbitrary algebraic equations is you're allowed to do arbitrary finite algebraic extensions. And Seidenberg embedding theorems, so it's a very simple consequence, it's a baby case of this theorem if you want, tells you that you can always move from one side to another. It's really not very hard if you prove something in the differential algebraic version to translate it in something about the functional approach and vice versa. Okay, so with this terminology in place, the problem of integration in finite terms, of Liouville problems, is the following. You start with an element from an elementary differential field extension, And the problem asks you to decide whether you can find some or any antiderivative. It doesn't change, it doesn't matter. If any or some antiderivative lie in some elementary differential field extension of the field of rational function. Okay, and if it does, you have to compute an elementary differential field extension and an antiderivative for this element. Okay, so two examples or three examples that I will base my talk on. First is the error function. So this is the most classical example. This is the simplest one to prove in practice. So if you want one example, you can look at this one. The error function is not an elementary function. Another example that it was very important for Liouville and which started the theory is the case of elliptic integrals. So an elliptic integral that is not degenerated in the sense that it's really an elliptic curve, they are also not elementary functions. Okay, all of this was proved by Liouville already. And the third kind of positive example to show you that it's not always a negative example. So if you look at indefinite integral of this form where you have a rational function of z and the square root of a polynomial, so exactly like the form of the elliptic function, but you ask that the curve defined by y square is equal to this polynomial has genus 0, okay, then this function is elementary, always. Okay. The reason is because you can choose a rational parametrization of your curve, and you can just make the change of variable by this rational parametrization, and then you reduce to a rational function. Other example is the Wallis indefinite integral. So there are many that you can compute, and there are many that you cannot compute. And Liouville's problem is to decide which one is which. So what are the tools at your disposal to study this problem? And so let me first make a comment about Picard-Vaisseau-Galois theory. So Picard-Vaisseau-Galois theory, of course, Liouville didn't have access to this technology, but you can say that it's not directly applicable to the study of this problem. So it doesn't mean it's not applicable at all. We will see that it's somehow applicable too. But if you try just to do the thing that is stupid, you just take the two equations. So the first one was the one appearing in the equation of the harmonic oscillator. The second one is the one appearing in the equation of the pendulum. Okay, so they have the same Galois group. Okay, they have the Galois group GA, but the first one is elementary and the second one is not. So how can you detect that? I mean, just say that in general, the kind of fundamental notion in Picard-Vaisseau theory is rather the notion of Liouvillean function, okay, which is obtained by closing the class of elementary elementary function under integration. But of course, the problem of integration in finite term for Liouvillean function is stupid because you just close under integration. Okay, so these two theories are somehow not completely compatible. The second thing is that, okay, if you, I mean, I taught several years the first course of calculus. I guess many of you did that too. And you all are aware that when you compute integral, there's a whole bunch of techniques you can use, and you never know which one to use. Okay, and so you can use substitutions, like in the case of genus 0 that I did before, integration by part for the Wallis integral. So it doesn't seem to be a common algorithm that goes through all these cases. Okay, and the key insight of Liouville is to find they say about the common feature, but a common feature of all such computation. Okay, and the common feature is the following. So it's a theorem of Liouville that if you have an elementary function, if the antiderivative is also an elementary function, then it's a very special form. It's always a rational function of your initial data plus a sum of weighted sum of your initial data. And when I say your initial data, I mean that you have to include the derivative of your function itself. Okay, and if you look at the example studied by Liouville in the previous slide, okay, they were all examples. So this one, the R function, it satisfies an order 1 equation. This one also satisfies an order 1 equation. So all the remaining term vanishes. Okay, you have all the higher derivative vanishes. And so the computations are much simpler in that case, and Liouville could handle them by hand computations. Okay, and so based on this theorem and making a lot of work, okay, Rich was able to obtain a full decision procedure. And here's the decision procedure that I display for you. It's the decision procedure for algebraic functions. So I take it from Davenport's book. So you can see here as an input, you are given the equation of an algebraic curve and a function on this curve. So you're really given an algebraic function. And the output is really what was required by Liouville. It's the integral of this function if it's elementary, the indefinite integral. And if it's not elementary, the output is just written not elementary. And so the comment is that Davenport makes is that this is in fact a perfectly workable algorithm subject to the definition of the subsidiary algorithm. Many of these, although their precise definition may appear strange, are perfectly familiar algorithms of computer algebra. Okay, but then it still says that the kind of complexity in the computations are very difficult. Okay, so it's not like these problems are easy to solve on a computer. This is still a very active area of computer algebra to improve on these algorithms. But from my point of view, I will consider that this problem is solved and we want to apply this decision procedure rather than to improve it. Okay, so now I will go to the second part of my talk, and is to change essentially the basis of the theory, the notion of elementary function. Okay, so the purpose of my talk will be to study the problem of integration in finite terms for another class of function, a model theoretic class of function, which extends Liouville's class of elementary function, and which is called the class of exponentially algebraic function. Okay, and the concept of, so just to give you a bit of history, the concept of exponential algebraicity in model theory goes back to the work of McIntyre and Zilber on exponential algebra. But in the difference with what I'm going to present, they are mostly interested in the case of numbers. Okay, and so in the case of the exponential field C with the exponential. Okay, in my case, the concept I will present to you is the concept of exponential algebraicity, which works for holomorphic and meromorphic functions. And it was developed later on by Wilkie and Kirby. Okay, and although it was developed later on, it is much better framework than the number theoretic framework. Okay, the function theoretic notions have several advantages over the number theoretic notion, and of course, we all know that functional transcendence is always easier than transcendence. Okay, so although the concept was developed later on, it has better properties. And so like for the notion of elementary function, I will present you two complementary approaches to define this notion. The first one is a functional approach, which rely on the notion of definability in a minimal structure, and this is essentially the approach followed by Wilkie. And then I will present you a differential algebraic approach, which relies on the action-rule theorem, which is the approach developed by Jonathan Kirby. But in contrast with the case of elementary function, you know, the equivalence between the two notions was just Seidenberg and Benning's theorem. Here, it's much more evolved than that. And actually, in the paper of Jonathan, where he studies this, there's 4 different equivalences. I'm just going to give you 2 of them. Okay. So let me start by what is an algebraic function before defining what is an exponentially algebraic function. And so I attributed the proposition to Wilkie because I don't know if it is before. If someone knows a previous reference to what I'm going to say now, please tell me, because I would be interested, but I don't know how to do that without using the work of Wilkie. And so the goal is to give another characterization of the notion of algebraic function. So the first definition is the one you're used to. So what is an algebraic function? It's an holomorphic function which satisfies a non-trivial polynomial equation with coefficient rational functions. Okay. The second definition, the second characterization that I'm going to give is that on some complex disk D, which is included in the domain of your function, actually the graph of your function, you can view it as a subset of C square. Okay, and you identify C square with R4, okay, and you ask that this subset, this graph, is a semi-algebraic set. Okay, it's given by a combination of real polynomial equations and inequalities. Okay, and the third property is that on some complex disk D included in U, so the fact of restricting the domain, now it's like for elementary function, we were also allowed to restrict the domain. So if you restrict the domain, the function or its graph, its equivalent, becomes definable in the structure of semi-algebraic geometry. Okay, so it's given by a first-order formula in this structure. Okay, so let me just explain what is non-obvious about this proposition, okay, and what is somehow quite obvious. So if you think about the first one, if you take an algebraic function in its usual sense, how do you show that the second condition is just that you use continuity of the roots, right? You may assume that your polynomial equation is irreducible, so the roots are distinct, and you will just use inequalities to distinguish the roots from each other. And from this, you will be able to define the graph of your function just using your equation and inequalities. Okay, the part that is highly non-trivial for me is that the second condition implies the first one. Okay, and the point is that you really want to work with, I mean, the notion of semi-algebraic set is a notion from real algebraic geometry. And so in order to prove it, you have to decompose your function and your variable in terms of real part and imaginary part. So the variable, I wrote it, z is equal to x plus iy. Okay, x is the real part and y is the imaginary part. The function, I wrote it u plus iv. Okay, u is a function of x and y, v is a function of x and y. And the assumptions that the graph of the function is semi-algebraic, it tells you that the graph of u and the graph of v are also semi-algebraic. This is really not very hard to see. Okay, but this graph, because it's a graph of a function, it has empty interior in C times R, which is R3. Okay, and so in one of, I tell you it's defined by polynomial equations and inequalities. There cannot only be inequalities. Okay, if there were only inequalities, then you will have something that has a non-empty interior. And so you can find two complex polynomials, okay, which vanishes on x, y, and u of x, y, on the real part and on the imaginary part, at least on some domain D. Okay, but this is weaker than what we want. We want to have a complex polynomial which vanishes when you apply it to x plus iy and u of xy plus iv of xy. And it is for this argument that I don't know how to do something other than what Wilkie does. And Wilkie has an argument, which is a very smart argument using Cauchy-Riemann relations, to show that from these two relations, you can indeed get such a polynomial, R. Okay, but the procedure to compute R from Q and P is not explicit. There's no explicit formula. So if someone has another proof of this thing, I would be interested. Okay, so you can see that, okay, what we are going to use as a basis of our definition of algebraic function is the third one. Okay, so what about the equivalence between 2 and 3? I haven't talked about that, but so it's a deep theorem, but it's a well-known theorem. It's Tarski-Seidenberg theorem that actually every definable set is semi-algebraic. Okay. And so the idea of Wilkie to generalize the notion of algebraic function is that instead of considering semi-algebraic geometry, you're going to consider ominimal expansion of semi-algebraic geometry. And by considering definability in these ominimal expansions, you will get a less restrictive notion of exponential algebraicity. And so in our particular case, we are interested in a notion of exponential algebraicity. And so what we do is that we add to a structure an exponential, the exponential function. Okay, so the problem is that if you add the exponential function entirely, your structure will not be ominimal. Okay, and so what you do is that you only add the exponential function on some ball, okay, around on some ball around 0 of radius 1, and because of the group properties of the exponential, you will get it on arbitrary large sets. Okay, so it's just arbitrary to have chose to reduce to the ball of center 0 and radius 1. Okay. And so what you do is you encode this function by taking a predicate in C2, which encodes the graph of this restricted elementary function. And of course, in that case, you won't get the exact analog of Tarski-Seidenberg theorem in the sense that you won't get this elimination theory. But in fact, you've got something that is as powerful for what we want to do, is that the theorem of Van den Dries. It's one of the first structure which was shown to be ominimal, which was not semi-algebraic geometry, is that this structure is a no-minimal structure. Every definable subset of the real line is a finite union of points and intervals. So although you don't have a good elimination theory, the tameness property of semi-algebraic geometry, they are maintained when you go to this function, to this setup. Okay, and so this is the main definition I'm going to use. So this is the functional approach to exponential algebraicity, is that we say that holomorphic function is exponentially algebraic by copying the previous definition from real algebraic geometry. If on some disk D included in this domain of definition, the graph of this function is definable in this structure. Okay, do you have questions about this definition? Okay, so before going further into why how to study this notion, I would like to explain why to study the problem of integration in finite term based using this notion rather than Liouville notion of elementary function. And so the first thing is that the class of exponentially algebraic function, first of all, it's a larger class. It's not hard to show, if you want, by induction that all elementary functions are stable under the implicit function theorem. Are exponentially algebraic function, but this class of function has an additional property, is that it is stable under the implicit function theorem. Okay, and to get this, we use the general property of functions definable in a hominimal structure. Okay, so this is a general fact that in a hominimal structure, the class of function you get will have this property. Okay, so the kind of simplest new example that we get of a function that is exponentially algebraic, but which is not elementary, is the Lambert function. So actually, it was already studied by Liouville, and Liouville shows that this Lambert W function, which is given by this power series expansion, okay, so I gave you the power series expansion at 0, it is, so Liouville shows that it's not elementary. Of course, it doesn't say that it's exponentially algebraic, it just says that it's not elementary. So the reason why it's exponentially algebraic is because it satisfies this functional equation. Okay, and so if you restrict to a neighborhood of 0, this functional equation will be invertible, and you can apply the implicit function theorem. This function is implicitly defined from this equation. Okay, and we say that the Lambert function is not a function that is not interesting. It appears in the solution of many problems. So this is a copy of the Wikipedia page about the Lambert function that I wrote here. So the Lambert W function branches, so cannot be expressed in terms of elementary function. That's what this is what was proved by Liouville. So it is used in combinatorics in the enumeration of trees. It can be used to solve various equations involving exponentials, the Planck, Bose-Einstein, and Fermi-Dirac distribution, and also occurs in the solution of delayed differential equations in biology and in biochemistry, and in particular enzyme kinetics. An open form solution for the time course kinetics analysis of the Michaelis-Menten kinetics is described in terms of the Lambert W function. So there would be there is a reason to try to generalize the problem of integration in finite terms to apply, for example, to such functions. And also to allow such functions, when you are integrating even an algebraic function, you would like to allow, for example, the Lambert function to appear in principle. Okay, and let me just say that in some sense, so this, I'm not going to make it very precise, but if you look at Wilke's article, he makes it precise. The class of exponentially algebraic, so making precise this is the main goal of Wilke's article. The class of exponentially algebraic function is the closure of the class of elementary function under the implicit function theorem. Okay, and actually, so this is why Liouville was interested in the Lambert function, because he already understood that the class of elementary function was not stable under the implicit function theorem, and so he had his own notion, which he called the fonction finie implicite, while the elementary function is what he called the fonction finie explicite. So this is one reason why to study the problem of integration in finite terms in this setup. So another reason, which is related to what I started my talk with, is that so both classes of function are stable under composition, okay? But the classes of exponentially algebraic function, it's also stable under taking local compositional inverses. Okay, so you have one more thing, is that you can take local compositional inverses. And one consequence of that is that you can make change of variables. Okay, so if you have a change of variables, so an holomorphic function from an open set U to an open set V, which is an isomorphism that you can invert, Okay, and if you ask that as an holomorphic function, it is exponentially algebraic. Okay, then performing the problem of integration in finite terms before the change of variable or after the change of variable is equivalent. Okay, so you get one operation that you can apply for free when you compute these kind of things. Okay, and if you think about the corresponding properties for elementary function, it's also not true. Okay, so if you try to integrate this function, the Lambert function divided by z dz, okay, so this function cannot be elementary because elementary functions are stable under derivatives. Okay, so if this function was elementary, the Lambert function will be elementary. So this function is not elementary, but if you apply to it an elementary change of variable, okay, you will get an elementary function. Okay, so in some sense, if you want to apply this kind of, in the class of elementary function, you can apply change of variables, which are algebraic change of variables, but you cannot apply elementary change of variables, but you can do it here. Okay, so this is one reason. And going further, this is how I motivated the study from the beginning. If you want to relate really the study of the pendulum to the study of this integral, okay, so then the equation of the pendulum admits an exponentially algebraic solution with energy H0 if and only if the integral is exponentially algebraic. Okay, so because of this definition using hominimality, we can perform the operation, the chain of operation I described you, and you can invert it. Okay, and so showing that the solution of the pendulum is exponentially algebraic is the same as computed the integral itself. Okay, so if you're able to show when an integral is exponentially algebraic or not, you will be able to show the equation of the pendulum. Okay, so here are two motivations for studying the problem of integration in finite terms from this perspective. Okay, so before going to the result, I would like to present the second version, which is the one we use in practice to do the proof. And this is the approach that is based on the Ax-Januel theorem. And let me say that the connection between the Ax-Januel theorem and the problem of integration in finite term is actually as old as the article of Rich about the solution of the problem of integration in finite term I started with, and with the Ax-Januel theorem itself. So the solution of the problem of integration in finite terms that I presented you is 1969, and the Ax-Januel theorem is 1971. And how Rich concludes his note in his thing is that I would like to express my indebtedness to Professor James Ax for his advice and suggestion during the writing of his note. And so clearly, Ax was aware of the connection between the Ax-Januel theorem and the problem of integration in finite term. So it's not a new idea, but it's the way we are going to exploit this idea that is a bit different than what is done classically. Okay, so I will explain what is the connection. So the Ax-Januel theorem, it's a theorem from functional transcendence. So I will phrase you one. So there are several equivalent versions. The simplest version for functions, holomorphic function of n variables, of one variable. So you take n holomorphic function of one variable, and you assume that they are Q linearly independent modulo C. Okay, this means that you cannot take a Q-linear combination of this function and get a complex number, something that does not depend on the variable C. Okay, and then it tells you, it gives you a lower bound on the transcendence degree of this function together with their exponential. Okay, and so often this theorem is stated over C, okay, and then there's a +1 at the end, according to how you state it. So here I stated it over C of Z, okay, and the bound is greater or equal to n. Okay, so what is the idea, which is the idea of Zilbert to define exponential algebraicity, is that actually to understand what are the exponentially algebraic function or even the exponentially algebraic numbers, if you assume that Januel conjecture is true. So for understanding what is the exponentially algebraic functions, what they are is that they are precisely the function that you can build from functions satisfying the equality case in this inequality. Okay, so this is how we are going to manipulate exponentially algebraic function. And so it's a theorem of Jonathan in 2010, which tells you that so an holomorphic function is exponentially algebraic in the previous sense, if and only if you can find a domain D contained in your open set U, and holomorphic functions which lives on this domain D. This function should be Q-linearly independent modulo C, and they should satisfy the equality in Ax-General theorem. Okay, and the function you started with, you can use it, you can write it algebraically in the usual sense in terms of this function. And I'm not going to describe you the full procedure, but this second procedure, you can write it completely differential algebraically. Okay, in the same way that you can make sense of, for an element in a differential field, you can make sense of what it means that it is an elementary element. You can make sense of an element in a differential field of what it means to be exponentially algebraic. Okay, and for me, it's a magical theorem, and all O-minimality things will disappear after we apply this theorem. Okay, the only thing we will use is the Ax-General theorem. So what are the main results? Okay, so what do we prove? So the main result, the first result, it says that if you start with an holomorphic function, so what I tell you is that there are many exponentially algebraic functions that are not elementary functions. Okay, and the question is, so how to measure the difference between the two concepts? Okay, and here what the theorem says is that if you assume that your function satisfies a linear differential equation whose coefficients are elementary functions, okay, then it is exponentially algebraic if and only if it is elementary. Okay, so I haven't written the model theoretic formulation, but the model theoretic formulation for those who know the language is that a function is elementary if and only if it's exponentially algebraic and its type over C of Z is analyzable in the constant. Okay, so the correct concept is analyzability in the constant. Okay, and so we first proved this theorem for the simplest case where you take y prime is equal to b of z, the equation when n is equal to 1 and there is no term in y. Okay, and we thought we proved a new theorem, and actually this theorem can be traced back to, okay, to Abel. Okay, so for just a comment, Abel comes before Liouville. Okay, so this theorem which relates exponential algebraicity to elementary function in the case where you just perform an integral, okay, was already known to Abel. And so the passage I took here is from a passage of the book of Singer and Raab, and it's written by Michael Singer. And he says that another generalization of Liouville's theorem stated by Abel is that if the integral of an algebraic function can be expressed in terms of implicitly or explicitly defined elementary function, and as I told you, modulo a theorem of Wilkie, this is exactly the concept of exponentially algebraic function, then it is elementary. Okay, so this theorem actually precedes Liouville's theorem itself, but we get it in a more general framework, okay, not only for integral of algebraic function, but first of all for integral of arbitrary elementary functions, and also for arbitrary solutions of linear differential equations. Okay, and so the direct application is that you can use all the work of Liouville to say that this function, so the error function, nope. Can you see? Can you see my screen still?
No, it's disappeared. Right?
Okay. Let me try to start again. Up. Up. Okay. And so this function that were studied by Liouville, so I wrote so the error function that appeared previously, the elliptic integral. So in the case of the elliptic integral, this goes back to actually to Abel. Okay. And so to Liouville actually. And the Airy function, okay, the Airy function was also shown by Liouville not to be elementary. At least this is what Rit is explaining. So not exactly the Airy function, but the techniques that is used to prove that the Airy function is not elementary, to conclude that they are not even exponentially algebraic functions. Okay. So here are other corollaries, okay, that goes a bit beyond the one that I presented you before. The first one is about integrating the Lambert function. So as I explained you, Actually, if you can look at the Wikipedia page about the Lambert function, there's many like exceptional case where people know that it's integrable. And actually, you can use rich decision procedures to, so if I give you a rational function of two variables and you want to determine if this integral is, this indefinite integral is exponentially algebraic, so in that case, you cannot directly apply the decision procedure because the integrand is not elementary. Okay, but you can still do it after a change of variable. Okay, and so you can apply the algorithm to cases where previously the decision procedure could not be applied. Okay, and so this is just applying rich decision procedure plus the theorem one to ensure that the conclusion, when you apply rich decision procedure, you can strengthen it into not exponentially algebraic, and then you use that the change of variable formula is preserved under exponential algebraicity. Okay. The second corollary is the example that I gave you, started the talk with, is the equation of the pendulum. The equation of the pendulum admits an exponentially algebraic solution with energy h0, exactly with the energy h0 is plus or minus omega squared. Okay, and the case, so it's when the elliptic integral degenerates. And the case where it's minus omega squared is the case of, if you think about the real locus, it's the equilibrium position of the pendulum in the bottom. And the case where it's plus omega squared, they are the solution that goes make one round around the pendulum, but infinitely slowly at the end. They just end up at the unstable equilibrium position and in infinite time. And this solution, it is known, if you look at the textbooks about the equation of the pendulum, that you can write them with arc sine of tangent. So they are the only ones, what the theorem tells you is that they are the only one that you can compute, that you can define in this minimal structure. Okay, so again, this is just Liouville's analysis of elliptic integrals plus the theorem one plus the stability under compositional inverses. And the third example, which somehow follows from the model theoretic formulation I alluded above, is that the differential equation satisfied by the Lambert function, okay, it satisfies an order one differential equation, it's strictly minimal. It's strongly minimal and completely disintegrated. So it's not the case. Again, every time you get a function that is an exponentially algebraic function that is not elementary, it's because it is not analyzable in the constant, and so you will get something that is not analyzable in the constant inside. Okay, and in some sense, it's the oldest example. Okay, modulo this theorem, okay, it was already shown by Liouville that this equation is strongly minimal. And so this is, in some sense, the oldest example of an equation that was shown to be geometrically trivial and completely disintegrated. Okay, so the second part, the second theorem, okay, so I have so not that long anymore, so let me go a bit faster. But the second theorem aims to replacing what Liouville's and Rich arguments do using computations of residues and Liouville's theorem by Galois theoretic arguments. Okay, and as I told you, you cannot always do that, but you can still, in many interesting and meaningful situations, do that. Okay, so you start with an holomorphic function and you assume two different things. You assume that it is exponentially algebraic, okay, and you assume that the function belongs to some strongly normal extension in the sense of Colchin of the field of rational function. And so then you can conclude several things about this function. And so the first thing is that then you can, so maybe not all elements in your strongly normal L are exponentially algebraic, but actually up to replacing L by a smaller extension, you can find some strongly normal extension with the property that every element in this strongly normal extension will be exponentially algebraic. Okay. The second property is that once you've done so, the Galois group that you get is a finite extension of a commutative linear algebraic group. Okay. And the third extension, which looks like Liouville's theorems, is that you can give essentially a presentation by generator and relation of this strongly normal extension, that you can find finitely many algebraic functions and complex numbers such that this L0 is contained in the extension generated by the logarithm of this algebraic function, the exponential algebraic this algebraic function, and raising this algebraic function to the power lambda. Okay, in the case of Liouville's theorem, there's only logs that appear. It's only a rational function plus a sum of logs. Okay, and the reason is that the Galois group is the additive group, okay, and the other two forms, they are related to the multiplicative group. So, okay, so I will just be short, but using this kind of Galois theoretic argument, you can show that these three functions that I wrote previously, the error function, the elliptic function, and the Airy functions, they are not exponentially algebraic, and you don't have to rely on Liouville's argument. You can just use Galois theoretic computations. So what you do is that you compute the minimal differential equation satisfied by these functions. In the first case, it's the affine group. In the second case, it's the additive group. And in the third case, it's SL2. Okay, in the case of the affine group and SL2, the theorem tells you that if they were exponentially algebraic, the Galois group had to be commutative linear. So these two are not possible. Okay, but in the middle one, it seems that the argument doesn't work. That's why I told you before. Okay, but now you can use that you can move from a function to a compositional inverse. Okay, from the elliptic integral, you move to the elliptic differential equation. Okay, and because exponentially algebraic functions are stable under this thing, you study the elliptic thing, and you show that this one has a Galois group an elliptic curve, which is not possible by the previous theorem. And finally, using the same thing, you can prove that the J function also is not exponentially algebraic. Okay, and so thank you for your attention.
Thank you, Rémi. Do we have any questions for Rémi?
I have one question.
I have, oh,
The argument for the I mean your last argument about the Galois group GA, it was too fast. Could you say it again?
So I'm saying that you replace so instead of studying, so the elliptic equation itself has a Galois group GA. This is not forbidden by the previous theorem. Okay, but now you look at the inverse function. Instead of looking at the function, you transform, this is an equation.
Oh, sorry, your Galois theorem is just an implication. Then it must have a Galois
Yes.
group. Sorry, I was puzzled by that.
Yes, it's just an implication.
Okay. Just an implication.
Yeah, yeah.
Okay.
Yes, so what you do is you just
Okay.
apply this argument, but to the function dz over dy. And this one has a solution in a strongly normal extension, and this Galois group is an elliptic curve.
Okay,
and so
thank
this
you.
is forbidden by the previous theorem.
Uh-huh.
And because elementary functions, they are not stable by compositional inverse, so you cannot make this argument with elementary function, but you can make this argument with exponentially algebraic function. So this gives a Galois theoretic proof that the elliptic integral is not elementary or exponentially algebraic. But I mean, the
May I
proof
ask
of
a second question? Could you give us a hint? Ah, sorry.
I think Charlotte will get back to you in 1 second. So maybe first Carlos question, and then Michael.
Oh, my question was Charles' question, so just give me. But thank you for a nice talk, Rémi.
Good. So I think maybe William has a question.
Yeah, I want to ask one quickly. If you look at the set of all the exponentially algebraic functions over as a set containing C of x, is that a field? Is it a union of strongly normal subfields? Do you have any idea what the Galois group or pro-Galois group is in that situation?
So if I look at in a differentially closed field at all elements that are exponentially algebraic, okay, in order to have an algebraic framework, the set of exponentially algebraic elements is a differential field. Okay, and what this theorem is telling you is that if you intersect this, so this is written, what you describe is written, I write it ECL of K, exponential closure of K. Okay, this set of exponentially element over K. Okay, and what the theorem tells you is that if you intersect it with KPV, the universal Picard-Vecchio extension associated to K, the Galois group of this is a projective limit of, I mean, it's abelian. I mean, it's a pro-algebraic group, but it's an abelian pro-algebraic group. Okay, plus a pro-finite part. It's a pro-finite part plus a pro-algebraic group. Connected.
Oh, right. I was interested in the strongly normal version of that. So I mean, without the just looking at the left hand of your intersection, is that do we know anything about that field?
About what?
Delta.
So in that case, it is not, it contains, I mean, it goes beyond Picard-Vecchio. I mean, this field contains elements that are not in Picard-Vecchio field or even in strongly normal field, strongly normal extension of K. The Lambert function is an example which is not in a strongly normal extension, but which is in ECL of K.
Thank you.
William, I think you had a question.
Well, I'm not sure whether that's a good question or not. In all the examples you gave, there is some change of variables involved. Is the notion of change of variables somehow algorithmic? I mean that you know that how to do it in some algebraic way, or I mean you can know somehow by looking at the function that you can use certain change of variables and to make it fall into the theory?
No, that's a good question. It's because I'm only showing example where there is a change of variable that works, because this is the only example that I know how to treat. You know, you could ask more generally, given an exponentially algebraic function, can I decide if the integral is exponentially algebraic?
Right.
Okay. And this is something that I don't know how to do. Okay. And I think it's very hard. So all the cases where I know how to do that, it's because there is a change of variable that reduces to an elementary function.
Right.
Or using
so that's kind of just an art, is that right? In some sense.
So I chose the example so that there is a change of variable, but I don't know how to find, given the example, I mean, I have no idea how to know if there is a change of variable that transform it into something that is elementary. This I don't.
Okay.
But every time you have one, you can apply the result here to compute it using Ridge decision procedure.
Right. Thank you. Very nice talk.
Do we have any more questions for Rémi? If not, let us thank Rémi again. Thanks, Rémi.